Hello and welcome to this part of lecture. So this is chapter number 8, second order circuits of our Sadiku's textbook. In our last lecture, we talked about or we solved the RLC series and RLC parallel circuits. We saw how we developed the second order differential equations for those circuits and how we solve those differential equations. For RLC series circuit, we saw that we solved the second order circuit for the current, and for the parallel RLC circuit we saw that we solved the RLC circuit for the voltage uh, across the inductor or the capacitor. Okay, and similarly we also saw that while solving these two circuits we develop a characteristic equation out, and we find out the roots of that characteristic equation, and with the help of those roots we find out the value of S1 and S2, and with these values and using the initial conditions we find the value of A1 and A2 for voltage and current, and in that way we develop the complete picture for the or the solution for the current or the voltage waveforms for these circuits. So today we'll be going into further detail about this response or this response of this circuit, or basically what we call it the current or the voltage response of the circuit, and see what are the types of these response and what are the things which determine these types. So we see that the solution of the differential equation or the characteristic equation which we saw in our previous lecture, s square plus 2as plus omega naught square, the solution for these or the roots, or basically this is a quadratic equation, or the roots of this quadratic equation are there are two roots s1 and s2, and these two roots are the solution for this characteristic equation, and this solution basically determines the type of the response for our RLC or second order circuits. So there are four types of response. Oh, sorry, I have mentioned three here. So there are typically four types of response, because these roots can be of four types. And these roots can be either real and distinct. It means that there will be two different values and real values of S1 and S2. These roots can be similar and real. It means that there are two similar values and real values for S1 and S2. These roots can be complex. It means that it has a real value and an imaginary value. And these roots can also be imaginary. It means that they have only imaginary values. So for all these four values, there are four different types of response for the characteristic equation or for our second order circuit. So these response are classified as overdamped response, and overdamped response comes when we have real and distinct roots. We have critically damped response. It comes when the roots are real and similar. We have an underdamped response when we have complex roots, and we have an oscillatory response when we have imaginary roots. So oscillatory response will not be covered as a part of this topic or is a part of this course. And this is basically the response that comes in our active devices or active circuit devices, or what you can say as oscillators, and they have these roots coming as imaginary. But we are not going to cover oscillators in this part of our course. So we'll not be going to talk about the oscillatory response, and therefore your book also not talks about the oscillatory response in this chapter. So moving ahead, for the series RLC case, we remember that we derived this equation IT A1 e raised to power ST S1t plus A2 e raised to power S2t. This one was the generic response. And if our roots are say S1, S2 are real and distinct, we will have this form of solution. Or in either way, we can say that our alpha is greater than omega naught. This will be our solution, and the graph for this solution will come or will look something like this. Remember, this is the solution for our characteristic equation. Critically damped response, it comes that when we have alpha equals to omega naught, and when our alpha is equal to omega naught, our real roots are real and similar. So we have two similar roots, and those two roots are real values. Okay. And then the third case, that is interesting one, where we have S1 and S2 belongs to complex numbers, or for complex number, remember we have plus j beta. It can be any complex number C. So alpha plus j beta, it is the generic form of a complex number. So we have our roots in this format, or you can say that alpha plus minus j omega d, where omega d is the damped natural frequency and omega d is given as omega naught square minus alpha square. Uh, so this is how our so this is how the roots for an underdamped system will look like, and our response a1 e raised to power s1 t will change to something like this: a e raised to power minus alpha t, where minus alpha basically is the damping constant, b1 cos of omega d t, and omega d is the damped natural frequency of our circuit, or of our the response damped natural frequency of our circuit in this case. Similarly, uh, we have the same response for parallel RLC circuit. The only difference you see here is the voltage, because parallel RLC circuit, we solved it for the voltage waveform or the voltage response, and for the series RLC circuit, we solved it for the current waveform because of the ease of solving of the differential equations which we got. And similarly, if you're going to compare these two uh, solutions, they are pretty much the same. The only difference is that for series, you have the current; for parallel, you have the voltage. So if we are going to compare these both cases for, so we have a parallel RLC circuit and we have a series RLC circuit. And if the circuit has an underdamped response, the criteria for that is alpha should be greater than omega naught. The alpha for a parallel RLC circuit is 1 over 2 RC, and for series RLC circuit, it is 1 by, so R by 2L, and it is 1 by, omega naught is 1 by under root LC, and this is the overall response. Same goes with the critically damped response. Critically damped response, we have alpha is equal to omega naught, and in that case, what we got, which we get is something e raised to power t a1 t plus e2 t. And similarly, for underdamped response, alpha is less than omega naught, we have these values remain the same. This is our omega naught is this, and our overall response comes something like this. Remember, another comparison, alpha is versus tau, or the time constant. This is the time constant for first order circuits. So remember that for a first order RC circuit, the time constant is RC, and for first order RL circuit, the time constant is L by R. So this thing, if we have to, write it, it would be something like this, and this is again something like 2 times tau. So in terms, if we have to relate the first order differential, or so the first order circuits, this is a factor that basically relates one of the key components which we saw, or the time constant in first order circuits. It is something that can be related to that first order circuit as well, that part as well. Although the time constant part is not exactly, you can say, the same in this second order circuit, but this is some sort of relationship that we can develop with the first order circuits. So let's solve a couple of questions and see how things go. So for on the first example, example 8.3 of your textbook, it says that in the figure 8.8, so that this is the figure, resistance is 40 ohms, the inductance is 4 Henry, capacitance is 1 by 4 Farad. Calculate the characteristic roots for the circuit. Is the natural response overdamped, underdamped, or critically damped? Okay. So first of all, for a series RLC circuit, remember, for a series RLC circuit, our alpha is R by 2L, and our omega naught is under root 1 by LC. So we know that for series RLC circuit, we have alpha is equal to R by 2L, and we have omega naught equals to 1 by under root LC. So just find out the value of alpha. So alpha is 40 divided by 2 times inductance is 4. So 40 divided by 8, we get 5. So alpha is 5, and our omega naught is 1 by 1 by under root. Inductance is 4 and capacitance is 1 by 4. Omega is 1. Again, radians per second. Alpha is seconds minus 1. Remember the unit for alpha. Alpha, we also have seen 1 by 2 times time constant. Time constant is given in seconds. So alpha is seconds minus 1. We can always say find the units in this fashion. So these are the two values. So we can see from here that alpha is greater than omega naught. So we know that for alpha greater than omega naught, our response is overdamped. So our response is, so alpha greater than overdamped 1. So our response is overdamped. Okay. So and for this, the response will look something like I of t a1 e raised to power s1t plus a2 e raised to power s2t. The response will look something like this, and we have to find out the values for S1 and S2. And remember, S1 and S2 is equal to minus this, minus alpha plus minus under root alpha square minus omega naught square. So it comes out to be alpha is minus 5 plus minus under the root 25 minus 1, or minus 5 plus minus under root 24. So my roots will be S1 will be minus 1.01. Sorry, not 1.01, 0. So if I'm going to solve this, it comes out to be minus 0.101, and my S2 will be minus 9.899. Okay, so these will be my roots. So if I have to write the value, I mean, since we are not given the initial conditions, we will not have to, further solve and find out the response. So this is how we solve this question. It says, so we have to find out the characteristic roots for the circuit. So we found out the characteristic roots for the circuit. We found, we also found out that the response of the circuit is overdamped. Overdamped? Yes, it is overdamped. So this is how a simple circuit can be solved and analyzed. So next question, it's example 8.4 of our textbook. In this example, it says that find I of t in the circuit shown in the figure 8.10. Assume that the circuit has reached a steady state at time t equals to 0 negative. So this is our circuit. So this is our circuit at time t equals to 0. The switch is open and our circuit remains after time t equals 0 is something like this. So there are two stages for this circuit. One is before time t equals to 0, one is before the switching, and one is after the switching. So let's draw both of them. Before switching, or you can say time t equals to 0, the circuit looks something like this. This is plus minus 10 volts. This is the resistance. The switch is closed. This is our switch. This is the capacitor. This is the resistor. This is again a resistor, and this is an inductor. So this is 6 ohms. This is 0.5 Henry. This is 0.02 farad plus minus V. This is 3 ohms. This is 4 ohms. So this is before switching, and what it looks after switching, or after t equals to 0. After switching, it looks something like this. So once it has been switched, so the capacitor, and so this is the circuit that looks after switching. 6 ohm, this is 0.5 Henry, this is 0.02 farad, this is 3 ohms, and this is the voltage we need to find out. So it says that in this circuit, we have to find out the current in this circuit. So we have to find the current in the circuit after after switching. After switching, we have to find out the current in the circuit. So first of all, what are the initial condition? Our first step is to find initial conditions. Okay, so in initial conditions, the initial conditions are number one, VC 0 negative. We have to find out, and number two, we have to find out IL 0 negative. We have to find out these two values as our initial conditions. So remember, this circuit is in this state for a long time. It means that the capacitor would have been totally charged and the inductor would be totally magnetized. So in this case, the circuit will look something like this. This is 10 volts. This is 4 ohms. A completely charged capacitor will act as an open circuit, and a completely magnetized inductor will look like or will act as a short circuit. Okay, so this is 6 ohms and this is 3 ohms. So now we have to find out what is the voltage. So VC0 is this voltage, IL0 is this voltage. So it's now we have to find out what is the voltage. So technically this open circuit voltage, so VC0, so VC0 is basically the voltage that is appearing across this 6 ohm resistor. So 6 divided by 4 plus 6, we simply use the voltage divider rule in multiply by 10. So it is 6 volts. You see at 0, or you can call it as 0 negative. Remember, since it's a capacitor, the property of capacitor is I C dV by dt. The voltage doesn't change instantaneously. Similarly, for an inductor, V L times di by dt, the current doesn't change instantaneously. So if we have voltage at 0 negative, the voltage will also be at 0 positive. And so it will be considered as one of the initial conditions. Similarly, if I have to find out the IL0 negative, it will be simply the current that is flowing in this branch. And the current flowing in this branch is simply 10 volts divided by the overall resistance, that is 6 plus 4, 10. That means that it is 1 ampere. So IL0 negative is 1 ampere. That is the current that is flowing in the circuit. So we have found out our initial conditions. So remember VC 0 negative is equal to VC 0 positive is equal to 6 volt. This is our first initial condition. Our second initial condition, IL 0 negative equals to IL 0 positive equals to 1 ampere. So these are our two initial conditions to start our question. Okay, so now moving ahead, now our circuit is switched. So after switching, that is T is 0, you can say T at T is 0 positive. Just after switching, the circuit is something like this. So this is our circuit. So this is my inductor. This is 0.5 Henry, or you can say that IL0 is 1 ampere. Initial condition 6 ohm is this resistance. This is my capacitor. This is 0.02 farad, and VC 0 positive 0 is is 6 volts, and we have this resistance as 3. So, and we have to find out this current I. So remember, for a series, this is a series RLC circuit. This is a series RLC circuit. So for a series RLC circuit, what we have to do is, we know that we have to find out alpha. And for a series RLC circuit, alpha is R by 2L. We have to find out omega naught. Omega naught is 1 by under root LC. So from this circuit, if we want to find out alpha, alpha is R. So the total resistance is 6 plus 3, 9, and inductance 2 multiplied by 0.5. So alpha is 9 seconds minus 1. So this is the value of alpha. And if I have to find out the value of omega naught, it is 1 by under root, so 0.5 multiplied by 0.02 the root. So omega naught is equal to 10. So omega naught is equal to 10 radians per second. So remember, the units are very important. If in the exam, if you're going to miss these units, you will be losing some certain points. So now the characteristic equation. Or you can just simply say solution for the characteristic equation will look solution will look S1 2 will be equal to minus alpha plus minus under root alpha square minus omega naught square. Okay, so when we have alpha and omega naught like this, and second thing, we know that alpha is less than omega naught. So alpha is less than omega naught. It means that the response of the solution will be under damped. So the response for the solution will be under damped response. Okay, so now let's find out the values for S1 and S2. So values for S1 and S2. So values for S1 and S2, just simply solve that characteristic equation. We get minus 9 plus minus j times 4.359. So these are basically two values. So one value, or we call it S1 as minus 9 plus j 4.359, and our S2 is minus 9 minus j 4.359. So these are the two values for S1 and S2, and we know that for for underdamped response. Remember, for underdamped response, the natural response of our current will look something like this. I of t, remember going back a few slides, this for underdamped response, our case is e raised to power minus alpha t b1 cos omega dt plus b2 sine omega dt. Okay. So for this case, we have e minus alpha t, call it a1 cos of omega dt plus a2 sine of omega d into t. Remember, and where omega d is under root of omega naught square minus alpha square, right? So if we find out the under root of this becomes equal to 4.539, this value. So this is basically our omega d. Both of these values are equivalent to omega d. So if now just put in the value, this is omega d and this is my alpha. So these two values are alpha. Again, this is same value as alpha, right? So just put in the values. So I of t will become e raised to power minus 9t a1 cos of 4.359 t plus a2 sine of 4.359 t. So this is your first case. So remember, it is e raised to power minus, so e raised to power alpha t. One thing we have to check, so e raised to power minus alpha t, so that is fine. So just remember your alpha value is 9. And so you do not confuse alpha as minus 9 and make a plus 9 here. It will really mess up your solution. So this is the the generic or the natural form or the natural response of the circuit. Now the step is, now we have to find values of A1 and A2. Okay, so the thing is how we are going to find out the values for A1 and A2. This is the new thing. So now let's try it. So now we know that the initial conditions were initial conditions. What were the initial condition? Initial condition was I0 as 1 ampere, right? And the second initial condition was V0 or the IL, the VC. So VIL or VC was 6 volt. Okay, so VC was 6, IL was 0. So first we know that I, or the current that is flowing, the response equation for an underdamped case, cos of 4.359 t plus A2 sine of 4.359 t. This. So now let's put the first initial condition. Put I of 0 equals to 1. Okay, so just put I of 0, replace t with 0, minus 9 0 A1 cos of 4.359 into 0 plus A2 sine of 4.359 into 0. So what we will get? I of 0 is 1, e raised to power 0 will be again 1. A1 multiplied by cos of 0 is 1 plus A2 sine 0 is 0. This. So we get from here that A1 equals to 1. So we get the value of A1. So now we need the second initial condition to find out the value for A2. So we know that we have used IL now. So for second differential equation, we know that VC is 6. So VC is basically C, or you can call it IC, is equal to C times dV by dt, right? So this is one of the case, or the other thing which we get here is that for an inductor, VL is equal to L times di by dt. So this is the second case which we have. So now remember that we have to find out this di by dt, or this value for or di by dt value. So since we have this I of t with us, and I of t is e power 9t, it is A1 cos of 4.359t plus A2 sine of 4.359t. So this is our I of t. So if we have to find out d by dt of I, we just simply differentiate it. So we will differentiate it and we will have a value. So if we differentiate it, we will get minus 9 e raised to power minus 9t A1 cos of 4.359t plus A2 sine of 4.359t. First term plus second term a power minus 9t. A1 cos of 4.593, it will become minus 4.359 A1 sine of 4.359t plus 4.359 into A2 into cos of 4.359t. Remember, because derivative of cos is minus sine and derivative of sine is cos. This is what we have done. So we have basically differentiated it. So now basically what we need di0 by dt. This is the value we need. So this is the value we need, and this value comes from this case, dvl and dt. So let's draw this circuit. So remember, this thing is acting as a voltage source. This is capacitor, inductor, and this. So this is the 6 ohm resistance. This is the 3 ohm resistance. This is having plus minus VC0, and this is having IL0, right? IL0 is 1 ampere, and we have VL as equals to 6 volt. So now what we have to do, we have to basically find out the rate of change of current di by dt by this. So inductor doesn't allow instantaneous change in current. So the current will not change instantaneously, but the voltage but there will be some rate of change of current that will be happening across this. So remember, in our previous lecture, we developed this form of equation where we said di by dt, or when we were solving this for a single order differential equation, we wrote this equation: 1 by IL R times I0 plus V0. Or in that case, we had 1 minus L R into I0 because of the initial condition plus V0. Remember, we wrote this thing, di by dt. Okay, so we found out this thing. So let me take you to that particular slide as well. So if we go and check our previous lectures, so this is the initial condition part which we developed for parallel RLC circuit, and similarly we developed a same equation for the series RLC circuit. So this equation will help us in finding out the second differential initial condition. So di0 dt. So we are basically using this equation from our previous lectures from source free RLC circuit, series circuit, and source free RLC parallel circuits, right? So we are using this. So coming back, this is that equation. So using that equation, we can find out di0 by dt, and with this becomes minus 1 divided by inductance. The value of inductance is 0.5 Henry, 0.5. Overall resistance is 9. Multiply by the value of current. The direction of current is this. So this is the again current, that it remains the same. Direction is current is 1 plus. Remember the voltage across the capacitor. The capacitor is charged to minus 6 volts. So the voltage across this capacitance is plus, and since it is you can say the current is moving out of the positive terminal, so the voltage is taken as negative. So it comes as minus 6. So overall this becomes minus 6 amperes per second. So the rate of change of current across this will be minus 6 amperes per second, or the rate of change of current across the inductor will be this. Although the inductor doesn't allow the current to change instantaneously, but since as time passes, the current will be changing with some value, and this is the rate of change of current that will be happening across the inductor. In other ways, you can also see that that if this inductor is acting as a short circuit, so all the capacitor voltage will be appearing across this inductor, and that is equivalent to the uh, uh, equal to the 6 volts. And since the inductance value is 0.5 Henry, so 6 volts divided by point, it would be minus 12 volts per second, and that gives you a rough estimate, but that is not the case. So you can't you just simply say, okay, fine, this capacitor voltage will be appearing across this inductor and divide it by 0.2, and you will be getting 12 volts per, or sorry, 12 amperes per second. So you can't, you don't have to do something like this. This is not the exact way of finding out the rate of change of current, because some of the students will make this mistake that they would say, okay, fine, this whole capacitor voltage will be appearing across this inductor and we can just simply, do this sort of thing. No, you have to use this particular equation, or this basically particular equation, to uh, evaluate this value. So now you have this rate of change with you, and you use this value or plug in this value into this differential, this equation. So now solving this, we get, again, I will write it for ease, di by dt equals to minus 9 e raised to power minus 9t a1 cos of 4.359 t plus a2 sine of 4.359 t plus e raised to power minus 9t a1, sorry, here now I have to add, this becomes minus 4.359 a1 cos, so it is sine 4.359 t plus 4.359 t, so 4.359 a2 cos of 4.359 t. This is how it goes. So now we put in the values. So at time at t equals to 0, di is 0 by dt is minus 6 amperes per second. So this value becomes minus 6 minus 9 e raised to power minus 9 into 0 plus a1 cos of 0 will be 1 plus a2, you can always neglect this term, 0 plus e raised to power minus 9 into 0 minus 4.359 a1 sine term, it will be 0 plus 4.359 cos of 0, and this is multiplied by a2. So this basically comes out to be, remember a1 we have calculated it as 1, so it becomes minus 6 into minus 9 a1 comes here, plus this goes to 0, and this we get a2 multiplied by 4.359 and multiply by 1. So eventually we get the value of a2, and the value of a2 we get is 0.6882. So this is the value of a2 we get. So our overall solution I of t for this case will become e raised to power minus 9t cos of 4.359 t plus 0.6882 sine of 4.359 t. This. So this is our overall solution, what we get, and this is our answer. So this is the base. So this is basically the response of the circuit, or the after switching, or this is the overall natural response of this RLC circuit, that once the circuit has been switched off. And this is a more practical realization of how actually these circuits behave in practical systems. So in practical systems, we can say that this is a transistor, and this transistor is switching on and off after a certain time. And if our time the switching speeds are low enough to charge or discharge these capacitors completely. So these will help us in overall determining the response of the circuit, and overall the natural response for an RLC circuit or source free RLC circuit will look something like this. So in this case, it will look something like this. So the next part, it can be that you have to draw this waveform E minus T. So the A1 value is cos 1, so 4.5 T plus 0.6882 sine of 4.359 T. So remember the diagram where this plot has been drawn. So this plot will be drawn between two envelopes, and it would be cos of this and this. So remember, this is the shape of this response. This will be the shape of this response, and it will look something like this. E raised to power minus t. So if this is e raised to power minus t, so this in our case will be e raised to power minus 9t, and this is the time period for this 2 pi divided by omega d. So let's try to draw the shape for this. So the easiest way is to see what happens at time t equals to 0. We put time t equals to 0, this term vanishes out, this term vanishes out, and this term. So we at time t equals to 0, we have a value equal to say 1 comes here, and e raised to power minus 9t at time t equals to 0 is also 1. So it will start from here, and it will start from here. It will go something like this, and this sinusoid, this it will remain like this. It will be e raised to power minus 9t. This is one envelope, and the period, the time period minus this. So this is the time period. This is 2 pi divided by omega d. So 2 pi divided by omega d is 4.359. So this is this value, 4.359, and this is your time. So you can say it as it's not exactly the time period, because this is dying exponential will keep on, the magnitude will keep on dying, and this magnitude keep on dying because of this damping factor of minus 9. So this is the way how you draw this waveform, or in a way you picture out how this response will look like. Okay, so moving ahead to our next question. So this is our next question, and in this question we are given with a parallel RLC circuit. So in a parallel RLC circuit, it has given us the initial condition V of 0, I of 0, given the values of inductance and capacitance, and it asks us to find out the cases for R equals to 1.923, R equals to this. So basically the value of R are different. So we have 3 different values for R. So let's find out. So it's up. This is a parallel RLC circuit. Okay. So the easiest way to go it, first of all, find the value of alpha. So parallel RLC circuit 1/2 RC. Okay. So this is the value of alpha, and the value of omega naught. Omega naught will be under root LC. So our value of omega naught will be inductance is 1, capacitance is 10 milli. So 1 multiplied by 10 milli. So in our case, the omega naught will be 10 radians per second. Omega naught will be 10 radians per second. And we have 3 different values of R. So first case is R 1.23 ohms. The second case is R equals to 5 ohms, and the third case is R equals to 6.25 ohms. So for first case, we find out the value of alpha. Alpha is equal to 1 by 2 into 1.392 multiplied by C 10 milli. So the R is equal to approximately equal to 26. The second case, alpha is equal to, if I find out the value, 1 by 2 into 5 into 10 milli, this value of alpha comes out to be 10. And in third case, alpha is equal to 1 divided by 2 multiplied by 6.25 multiplied by 10 milli. So in third case, my value of alpha is equal to 8. Okay. So in this case, we see that alpha is greater than omega naught. In this case, we see that alpha is equal to omega naught, and in this case, we see that alpha is less than omega naught. So our first case, we will be having, what would be the response? So remember this slide or the summary slide. So alpha greater than omega naught, we have overdamped response. Alpha equal to omega naught, we have critically damped response. If alpha is less than omega naught, we have an underdamped response. So now just simply say that here we have the first case, we have alpha greater than omega naught. What will be the response type? So we have an overdamped response. Overdamped. So alpha equals to underdamped, we have critically damped response. And third case, alpha less than 0, we have underdamped response, right? So we have solved our previous question for an underdamped response. So let's give it a try for, say, critically damped response. Okay, so let's give it a try. So we are solving for R equals to 5, where alpha equals to omega naught equals to 10 radians per second, or 10, just simply 10, because alpha equals to omega naught, the units are not the same. So for alpha is 10 seconds minus 1, and this. So but anyways, so first part will be find out the roots for characteristic equation. Okay, so our roots for the characteristic equation, S1 S2 equals to minus alpha plus minus under the root alpha square minus omega naught square. So remember, this will alpha omega naught cancels out. This is minus 10. So the roots S1 and S2 both are equal to minus 10. Okay, so the response, number 2, response. So we know that the response will be of voltage response. So V of t for a parallel RLC circuit. So the response will be of voltage response. And for voltage response, we know that we have both roots are these are real and similar. So we have critically so this is critically damped response. So in this case, we have e raised to power minus alpha t a1 plus a2 t. So this is the critically damped response case. So our v of t will look like e raised to power minus 10t a1 plus a2 into t. This is how the response or the natural response will look like. Our third step is to find out, find the values for A1 and A2 using initial conditions, right? So initial conditions, we have I0 equals to 0, and we have V0 equals to 5. So in this case, remember, we need v of t as a raised to power minus 10t a1 plus a2 t, right? We need v of t, and we have one v of t, and we also need dv t 0. We also need this case. So this case for a parallel RLC circuit, remember the equation which we developed in our previous lectures. So I am going again back to the same slide where I showed you that equation, and that equation is this dv0. This is 1 divided by v naught divided by v naught by r, or that is the case of our initial uh, uh, condition case, or the uh, resistance, the value which we got over here. Okay, so coming back to our case, so we know that um, dv by dt at time t equals to 0 is minus 1 by c. We get v0 divided by r plus I of 0, right? So this is the equation we get. So if we put in the values, so it will be minus 1, the capacitance is 10 milli, v0 is 5, capacitance voltage divided by the resistance. The resistance in this case is 5, plus I0 is 0. So 1, so and this is, so d by dv by dt at time t equals to 0. This value comes out to be minus 100 volts per second. Okay, so this value is taken from here. So now we have both initial conditions. So we have this equation, we have this equation. So now we are using these two to solve our case. So first part, v of t, again from my it is minus t a1 plus a2 t. So at t equals to 0, v of 0 e raised to power minus 10 0 a1 plus again a2 goes to 0 because it multiplies by 2. So a1 becomes equal to v1 of 0 is 5, so a1 is equal to 5. So now dv by dt, if I derivated, it's minus 10 e raised to power minus 10 t. A1 is 5 plus a2 t plus e raised to power minus 10 t. A1 derivative 0, again a2t is a2. Okay, so this is my case. Or if I put the at t equals to 0, this value becomes minus 100. This value becomes minus 10 e raised to power 0, 5 plus 0 plus e raised to power again 0 into a2. So now a2, from here we find out the value of a2. This is minus 100 minus 10 into 5 plus a2. So a2 will be equal to minus 50. So a1 is 5, a2 is minus 50. So from here, what we get if we are going to solve, so we have v of t e raised to power minus 10t, a1 is 5, and a2 is minus 50 t. So this is the response for our case, and this is the critically damped response. So this is how the response will look like. Okay, so again, the next question can be, if we have to plot this response. So you can say this is 0.5 seconds, this is 1 second, this is 1.5 seconds, this is 2 seconds. Again, This is 1 by RC. So alpha was equal to 10 in this case. So 1 by 10 is 0.1 seconds. So during 0.1, so the graph will look, say at time t equals to 1, this point it will be almost equal to 0. So this is 0. So at time t equals to 0, so 0 it will be 5, value is equal to 5. So at time t equals to 0, the value will be equal to 5. And this value will drop to a value, and remember this this value will go below 0 as well for time, that is if it's less than 1.2 seconds. So it will be like something like this. So it's a critically damped response, go something like this, and it will start coming back before 0.1 when it's much earlier. So it will be something like this. So this will be the waveform, much smaller, but so it will approach to value of 0. Okay, and the minimum value will be, again, if you have to find out the minimum value for this, put d by dt equals to 0. So you differentiate it, dv by dt. So if we differentiate it, we get minus 10 e raised to power minus t, minus 10t, and this is equal to 5 minus 50t, and plus e raised to power minus 10t, and 5 zeros, so it is minus 50. So what we get is minus 10 e raised to power minus 10t, 5 minus 50t, minus 50 e raised to power minus 10t. So we just simply do the math and put d by dt equals to 0. It will be minus 50 e raised to power minus 10t, again minus 50 e raised to power minus 10t, and plus 500 e raised to power minus 10t multiplied by t. So we get 0 equals to minus 100 e raised to power minus 10t, and we have first 500 t e raised to power minus 10 t. So we have to find out the value of time when this equation is equal to 0. So we basically have to solve this case. So one case is e raised to power minus 10t. If we take common, so minus 100 plus 500 t, and this is equal to 0. So this is the equation which we get. So e raised to power minus 10t, when it will be equal to 0, and we have 500 500t equals to 100. So time equals to 1 by 5 seconds. So around 1 by 5 seconds, this value will or 0.2 seconds, this value will be approaching to its maximum value, because this at time t equals to this. So this is approximately 0.2 seconds. So this 0.2 seconds, around about this value will be maximum value, and this maximum value will be equal to, or will be approaching to near to 1, something around. So this. So I mean, I have basically used the concept of maximum and minimum from for any waveform, how this maximum and minimum can be found. So if this t is 0.2, just put in the value of 0.2. So if we put t equals to 0.2 in this equation, what is the value of v of t we get? So we get some value of minus so again, I mean, I'm just if I try to let's try to calculate it. So v of t equals to 0.2 seconds. This is e raised to power minus 10 into 0.2, 5 minus 50 into 0.2, right? So this is e raised to power minus 2, 5 minus 10. So e raised to power minus 2 multiplied by minus 5. So if we are going to find out this value, let me calculate it for you as a calculator at the moment. So E minus 2 is equal to 0.7182 multiplied by minus 5, so minus 3.59. Okay, let's see how it goes. Into 0.2. So, I mean, this is how you can find out this value. So this value is V of t at 0.2 is equal to minus 3 point, so multiplied minus 5, 3 point something something. So the minimum peak will not go till 1, but it will go to 3 point something something. And then from there, I mean, you can just see what the value it goes. So it basically approaches to 0 as time moves close to 1, and so on. So this is how you basically plot the graph, or overall get an idea of how the graph will look like. So you basically find out the value for which the maximum or the minima exists, and for that maxima and minima you have to you will get an idea of the or the picture of the graph. So again, if remember, the alpha in this case is 1 by 2 times RC. So the RC for this case, RC or the time constant or the equivalent we got. So R was 5 ohms and capacitance was 10 millifarad. So the time was 50 millifarads, and sorry, 50 milliseconds, and 50 milliseconds is again 50 into 10 x power minus 3. So this is around about 0.05 seconds time, and multiplied by 2.1. So this is 1 by 2 tau, you can say, in certain cases. And tau, if we compare it with the first order circuit, the tau will look something like this. So again, 0.05 millisecond would be an interesting time in this case. And this waveform, put t equals to minus 0.05 and see how it goes and where exactly it takes you. So let's try it. Again, it's an interesting thing. T equals to 0.05 seconds. So we have e raised to power minus 10 into 0.05, 5 minus 50 into 0.05. So let's see where exactly it takes us. So e raised to power minus 0.5, 5, so 50 multiplied by 5 divided by 100. This 5152 minus 2.5. So this is basically e raised to power minus 5 multiplied by 2.5. So e raised to power minus e x power minus 0.5, and it is 0.6 and multiplied by 2.5. This is some around 1.513 volts, and 1.516 divided by the maximum value 5. What did we get? So we get around 30.36. So if we just simply divide 1.516 divided by 30.36. Oh, sorry, 1.516 divided by 5. So you get around 30%. So what happened after this time? So after this time, whatever the actual voltage that was there, only 30% of the voltage has been is remaining, and that is something that can be related to, because in our charging or discharging of first order circuits, we lose so either we charge up to 63% of that value, and the remaining value is 30 around 27 or 30%. So again, this is something in the similar ballpark which can be compared. So that is how, I mean, a relationship between time constant of first order circuits and its relationship to second order circuits can be found in a manner like that. But again, these are for just back of the hand or back of the hand calculations. But other than that, I mean, this is how you solve a circuit and you draw a graph of this circuit, something like this. Again, this goes further below than -1. So here I stop this lecture for today, and from our next lecture we'll talk about the step response of series and parallel RLC circuits. So thank you very much for listening.